All right, so this is lesson 14.3, partial derivatives. That's actually kind of the whole scope of the entire chapter of chapter 14. Um, this is probably one of my favorite sections. It does have a lot of algebra in it, which is kind of why I like it, but it's also, this is a real throwback to Calc 1 um, with derivatives. But it is called partial derivatives because we're dealing with multiple variable functions. So um, let's take a look at how to interpret a partial derivative, and then we're going to get into doing them. I think doing them is actually pretty easy to do overall. It takes a little bit of getting used to, being careful, but I think you guys can pick it up pretty quickly. Okay, so what we've got here is a temperature humidity index. And basically what this is a heat index. I'm sure you guys have all heard that before. Heat index. Oop, I'm not writing anything. Why am I not writing anything? That looks good. Let's see. There we go. Heat index. Heat. Heat. Stop writing. What is going on? This tends to happen and I don't understand it. There we go. I do this every time I try and do this from home. I'm doing this from home and there's a little button on the pen, and if I push the little button it actually pauses my writing, so gotta watch what I'm holding the pen here. Alright, so this is called the heat index, and we're just going to call the heat index I. And you guys have all heard of a heat index. You know how sometimes it's a certain temperature outside, but it feels like it's a lot warmer than it really is. And that's kind of what this chart is showing us. Now it gives us this chart in Celsius. We're all used to Fahrenheit, but you know, it's the same general idea. We'll deal with it. So what you have over here is you have your Celsius, your temperatures in Celsius, and then up across the top here you have the relative humidity. So your temperature's on the left, your humidity's on the right. And so like if you can kind of take a look at this, and you know, it says that if the temperature is 34 degrees Celsius, if you come over here and the relative humidity is 50%, then it feels like 84 degrees Celsius. I don't know if that's right, but that's really big. That's a big jump. 50 degrees difference. I don't know. Maybe this is supposed to be in degrees Fahrenheit and this is Celsius. I'm really not sure. Um, anyway, the general idea is pretty easy to understand, that the humidity or the heat index, how it actually feels outside, is dependent upon both the degrees and the humidity. So there are two independent variables here. So my heat index is going to be a function of both the temperature and the humidity. So I is a function of T and H. And this heat index, again, you should have a general idea. It's very much like our wind chill, and we're actually going to do one with a wind chill factor in there as well. We did the one where, you know, the temperature and the speed of the wind affects how it feels outside as well. Same idea. All right, so what we're looking at here is um, the whole idea of a partial derivative has to come back to slope. And if you guys remember that when you're dealing with slope, we're used to dealing with a change of y over change of x, but if you think about it in two dimensions, y is typically going to be your dependent variable, and that's what slope is. Slope is always going to be the change of the dependent variable over the change of the independent variable. In this case, it's the change of the heat index over the change. In this case, we have two independent variables, temperature and humidity. So if I was to say something like, um, I want to find the partial derivative, or how the heat index, whoa, that's really thick. Let's get rid of that. Let's go to a thinner line. Um, I want to find how the heat index changes how the heat index changes at 28 comma 50. So what I'm looking for is I'm looking for what is the derivative. Oh, I'm sorry, I forgot to put the little sub t down here. So what I'm trying to do is I'm looking for the partial derivative of the heat index with respect to the temperature. So what I'm actually saying is if we were to hold the humidity constant at 50 degrees, so this is going to stay constant. That can be thick, that's okay. That's going to stay constant. I want to know what the change in the temperature is, how the temperature is going to affect the heat index at when the heat index, I'm sorry, when the temperature is 28 degrees if we hold the humidity constant at 50. That's what this is saying. So this little sub t there, that's what that means. So this is going to be the derivative with respect to t while holding humidity constant. Alright, so if I give you the dependent variable here, sub one of the independent variables, it means we're going to hold the other variable constant. We want to know what the derivative of the heat index is, or how the heat index changes with respect to temperature if we hold the other one, which in this case was just humidity, constant. So if we look at it at 28, so let's see here. Let's go with a highlighter. Boy, I'm not sure how any of these are going to show up. Let's try yellow first. So what we're looking at is, here is the 50 degrees. This is we're going to hold constant. It's kind of hard to see over top of the yellow, but that's the idea. We're going to hold that constant. You know what? I don't like that. Let's try a different color. Let's try, boy, all these colors are on there. Let's try purple. So here's 50 degrees. That's really, really bad. All right, we're going to do it a different way completely. All right, here's 50 degrees. That's better. It's a horrible circle, but it's going to look much better. All right, try this again. There we go. All right, if we hold 50% humidity constant, we want to know what the change is of the heat index based upon um, the temperature. And the temperature we wanted was 28 degrees. So here's 28 degrees. This is the row that we're looking at. And so what you can see is that when it's 28 degrees and 50% humidity, it feels like it is 76 outside. That's what it's saying. But we want to know what the rate of change is. So what we have to do basically, because we don't have an actual function, we have a table of values, we have to take an average slope between 2 points. And it doesn't really matter if you were to go from 26 to 28 or from 28 to 30, but the temperature is changing, the humidity is not. So we can take, I'm just going to do between 28 and 30. So if we did that, what we're looking at here is that I sub t, or the partial derivative with respect to t of 2850 is going to be approximately equal to, well, let's see, what's the change here? The change of the heat index goes from 76 to 78. So that's 78 minus 76, and then the change of the degrees goes from 28 to 30, which is over 30 minus 28, which of course gives us 78 minus 76 is 2 over 30 minus 28. So that's going to be 2 over 2, or 1, which is going to be, let's see, it's going to be a change of 1 degree Celsius per, I don't know, degrees Celsius. I don't know if it's supposed to be Celsius or not, but that's what you're going to get. So you're going to get 1 degree change of the heat index per change of the actual temperature if we were to hold the humidity constant at 50 degrees. And what we call that, let's scroll down a little bit. What we call this is the I sub t is the partial derivative of I with respect to t. And then you could also figure out if you held temperature constant, you know, and said that maybe I want to hold the temperature at 32 degrees, what would be the change in the heat index if I wanted to say maybe at 40 degrees or something like that. And then instead you would hold this row constant and you would do a change vertically like this in this column with the change up here in the relative humidity. So you could do it that way as well. Hopefully I didn't kind of babble my way through that one too much that you couldn't understand it. A little bit of notation. And this is where things get just a little bit different than in 2 dimensions. It's the same type of notation, but slight difference. So if we wanted to do the partial derivative of the heat index with respect to time, that would also be indicated just like you did a dy, dx, and stuff like that in 2 dimensions in ABBC calculus. This is going to be the derivative of I with respect to time in the notation, but look at how it changes just a little bit. I am purposely not drawing my D's as solid D's. They almost look like backwards 6's. It's a good way to describe it. This is a partial derivative notation. So it's the partial derivative of I with respect to time. Or if I wanted to do the partial derivative of H, of the humidity, then that would be the partial derivative of I with respect to H. Okay, these are Leibniz notation as opposed to prime symbols. So this is what we're going to use quite frequently when we are talking about partial derivatives, one of these 2 notations. All right, let's get off of this page. Let's try one more with a chart. And this one actually does go back to wind chill. So let's see, it says the wind chill index W is perceived temperature when the actual temperature is T and the wind speed is V. So we can write the wind chill as a function of the temperature and the wind speed. Now we've done something like this before. I can probably use a highlighter on this one, it'll be much easier. So let's see, the following table of values is an excerpt from a table in section, it says 15.1, it's actually 14.1 in your book. Let's go ahead and fix that. Alright, so here's our temperature in degrees Celsius. Here is the wind speed in kilometers per hour. Letter A, and there's actually a B and C, but I'm going to have to write them in because I didn't get them on the page here. Estimate the values of F sub T of negative 1530. Now what does that mean? That means we want to estimate the change of the wind chill when we take this with respect to time. So what we're going to, I mean not time, temperature, we're going to hold the wind speed constant. And the wind speed in this case is velocity, so this is going to stay constant. So we're really looking at, really looking at holding this, that's much better. That's going to stay constant, we're not changing it. We want to see what happens, however, when we take a difference, some kind of a slope, when we change the temperature. And we want to start when the temperature is 15. So again, it doesn't really matter if you go from -10 to -15 or -15 to -20 or something in that range right there. Um, Again, I'm going to go ahead and go from -15 to -20. So, oops, I'm going to use these two right there. So I got to look at the change. Scroll down just a little bit. So F sub T at -15, 30. Again, 30 is being held constant. Is approximately, so we're looking at the change here between -26 and -33. So from -26 down to -33 is really a change of -7, and it's going to be over the change of the temperature, which is -15 to -20, so that's a change of down 5, which is going to be 7/5, which means, what's that? 7/5 is 1.4 degrees Celsius per degree Celsius. So what this means is when we hold the wind speed constant at 30, a slope or approximate slope or change of the wind chill at -15 degrees is going to be about 7/5 or 1.4 degrees Celsius. So as the temperature decreases by 5 degrees, if we hold the wind speed constant, the temperature is going to feel like it's changing at a rate of 1.4 degrees. That's what that's saying. And then it says, let's do this for F sub V of -1530. Well, now that means I'm taking the partial derivative of the wind speed, which means I'm going to hold temperature constant at -15, so it's not going to change. So if I hold the temperature constant at -15, now I'm talking about holding this whole row right here constant. It's not going to change. And if the temperature here doesn't change, I'm only looking at a change of the wind speed. So the wind speed is going to change from -26 to -27. Again, I'm just going to kind of use these two. We could have used 20 to 30. I'm going to use 30 to 40. So the, sorry, not the wind speed is changing. The wind chill is going to change -26 to -27. So that's down 1 over the change of the wind speed, which looks like it is a change of 10. So really what we get is -0.1 degrees Celsius per kilometers per hour. That's an interesting one. So that's really degrees Celsius hours per kilometer. That's weird. Excuse me. Okay. Right, so hopefully you're understanding at least what's happening there. You're holding one thing constant and you're changing the other one, and it's always going to be your dependent variable divided by your independent variable. That's your slope holding one thing constant. It's a partial derivative. Derivatives are slope, partial slope. You're only seeing what happens if you hold the other thing constant. All right, part B that we want to do here is, in general, what can you say about the signs of the partial of W with respect to T and the partial of W with respect to V. So what we're trying to figure out is this positive or negative? Is this positive or negative. We're basically trying to figure out if the slope, the partial with respect to t is positive, or if the partial with respect to t is negative, and the same thing with wind speed. So let's take a look. This one was the partial with respect to t, and it looks like that if we were to hold wind speed constant, looks like for the most part the temperatures here are decreasing. It's going down, going down, going down. Doesn't really matter which one I hold constant. All the temperatures are going down. So we would expect that the partial with respect to t well, actually, I take that back. The temperatures are going down, but if the temperatures go down, when the temperature goes down, boy, I think I'm really messing this one up here. I'm trying to explain this and I'm fumbling on my words. We would expect that the wind chill, the way it feels outside with the wind, as the temperatures decrease, that we would feel like it's going to expect to feel colder. So really what you're getting is a decrease in wind chill and a decrease in temperature. So if you have a decrease of wind chill divided by a decrease of temperature, or just the other way around. No, I had that right. Decrease of wind chill divided by a decrease of temperature, and negative over negative, you would expect the slope to be bigger than 0. It should be positive. And then vice versa, if we took the wind chill and the velocity, so take the wind speed, and as the wind speed increases, you would expect the temperatures to get colder. So as the wind chills get colder and the wind speed gets greater, you're going to actually have a negative slope because you'll have a negative divided by a positive. So this should be less than 0. And then part C, and this is where we're going to finish this video. We're going to have probably at least one more, maybe 2 more videos on this one because I'm trying to keep them under 25. What appears to be the value of the following limit? What appears to be, writing too fast, the value of the following limit? And what we're looking at is the limit as v approaches infinity of the partial of w over the partial of v. What does that appear to approach? So what this is saying is as the wind speed gets incredibly big, what do we think is going to happen to the wind chill? Well, if you kind of look at it, as the wind speed gets higher and higher and higher, obviously the wind chill factor goes down, but it appears to be starting to level off. Negative 18 to negative 20 to 21, 22, 23, 23. Maybe if you put a column of 100 out here, it's still around 20, negative 23. I don't know that for a fact, but it appears to be leveling off. Same thing here, negative 24, negative 26, negative 27, 29, 30, 30, it's leveling off. Same thing here, starting at negative 30 down to negative 36, negative 37, starting to level off, negative 37, starting to level off here. So the idea is at a certain point in time, the wind speed is no longer really going to have an effect on the wind chill. After a certain point in time, the wind speed's not really going to affect it at all. So this is going to start to approach 0. Okay, the change of the wind chill as velocity changes is just, it's going to start to be basically nothing. The wind speed is going to have no effect as it gets really, really, really far out here. Of course, the wind's probably going to be held up by nature. There's only a certain amount of speed a wind can go, but all right, so that's the idea behind those. Again, I hope that wasn't too awfully confusing. I apologize for kind of babbling on about some of those things. The rest of this, I promise, will be much easier, much easier to follow. All right, we'll come back with a second video, maybe 2, depending on how long the other 2 take.